Hello and welcome to this video. We are going to talk about homogeneous linear systems. Recall that we are studying linear systems in the form Ax is b, and when we looked at a simple example with real numbers, then we figured out that such system can have either no solution or exactly one solution or infinitely many solutions. It is very interesting why there are only these three cases possible and there are no other options. And homogeneous linear systems are the key in answering this question. The definition of a homogeneous system is very simple. It is the system of the form Ax is 0. In other words, the right-hand side of the linear system is a 0 vector. Now here's my claim. I claim that a homogeneous system always has a solution. My question to you now, is this claim correct or not? Think about it and then we'll continue. This claim is of course correct because if we take x to be a 0 vector in Fn, then we will have a times 0 is 0. In other words, the solution x1, x2, etc. xn is 0 is always a solution of a homogeneous system. Since this solution is always there, we call it a trivial solution. And then a really interesting question is there also a non-trivial solution? This question is then a very important question for homogeneous systems. And you will see that all the theory that we have learned about transforms will be useful to answer this question. We will discuss the result on the next slide. The result is formulated in Theorem 3.8. This theorem is about the solution set of a homogeneous linear system. And the claim of the theorem is that this solution set is nothing else but the kernel of the transformation LA, and therefore the solution set is a subspace of Fn, and moreover the dimension of this solution set is n, which is this n, the number of variables, minus the rank of the matrix A. Now this theorem answers the question about the number of solutions, at least for the homogeneous system. Why is that? Because the theorem states that the solution set is a subspace. Now recall subspaces of Rn, for example, that could be consistent just from a 0 vector and then we have only trivial solution, but they can be also line, plane, or subspaces of higher dimensions, and they all will contain infinitely many solutions. And then we see that there can be only one solution or infinitely many solutions of a homogeneous system with unknowns in Rn. We will first prove this theorem and then we will look at an example. The theorem consists of two statements, 1 and 2, and the proof of each of them is in fact one line. We will start with 1, and 1 actually follows directly from the definition of the kernel. Recall that the transformation LA from Fn to Fm is just a left matrix multiplication, and then if we write the kernel of LA, then we can write that the kernel consists of all vectors S in Fn such that As is a 0 vector. But that is exactly the solution set of the homogeneous system. Next, we know that the kernel is a subspace of Fn, and since this kernel is exactly equal to the solution set, we can conclude that the solution set is also a subspace of Fn. It now remains to prove 2, and this must sound very familiar to you. So my question to you is, what result will you use to prove it, how you will use it, and can you actually complete the proof? Try to write down the proof yourself, and then we'll discuss it together. Of course, we are going to use the dimension theorem, and we apply it to the transformation LA. Then we have that n is equal to the dimension of the kernel of LA plus rank of LA, and the first is the same as the dimension of the solution set, because we just proved that these two sets are the same, and the second one, by definition of the rank of a matrix, is a rank of A. And then the theorem is proved. Notice how quick was the proof when we applied our knowledge of linear transformations. I can also imagine that this result and the proof may look a little bit abstract to you right now. I hope it is clear how this statement implies that there will be either one or infinitely many solutions. As for more feeling to this result, when we start actually solving linear systems, you will develop much more feeling why this result is true and how you can interpret it in numbers. At this moment, to make this theorem a little bit more clear, let us look at one small example. This is our matrix A. We have two equations and three unknowns, and we want to solve the system. Ax is 0. In this case, our 0 vector will be two-dimensional. It is also very easy to check that the rank of the matrix A is a number of its linearly independent rows. These two rows are linearly independent because they are not multiple of each other, therefore the rank of the matrix is 2. Then, according to the theorem, we expect that the dimension of the solution set will be the number of unknowns, which is 3, minus the rank of the matrix, which is 2, so the dimension of the solution set should be equal to 1. This is an example of a solution, and let us check that it is indeed a solution. What we do here, these are the numbers that we are going to substitute into the linear system. The coefficients of the first equation are 1, 2, and 3. I have written them here. And now I substitute my solution S, and you can easily check that this indeed is a correct equality. Now my second equation will have these three coefficients. I wrote them down here, and if I substitute my S in it, then also I get a correct equality. Therefore, my S is a solution. Now my question to you is, what are the other solutions, and of which form these other solutions will be? Think about it, and then we'll continue. It is not difficult to check that if we take some number t multiplied by our solution S, then it also will be a solution for any t in R. Then how do you write the solution set? Solution set in that case can be written as t1 minus 2, 1 for all t in R. Geometrically, this is a line that goes through origin and the point 1 minus 2, 1. It is a one-dimensional space, exactly as the theorem suggests, and it does contain infinitely many solutions. I hope that this theorem and its proof and the example were clear. Thank you very much for your attention.